are two-dimensional surfaces, right? So the little CMOS sensor in your smartphone that's detecting your light to form you the pictures, right, that you snap in your with your cell phone camera, or right in a ultrasound transducer or an MR system. They're all just these planar detectors. As an overview, and I showed this last class just to finalize our review, there's all sorts of things you can model under those assumptions. How radiation propagates, right, spreads out across space. How it might diffract, right, wave-like effects through different smaller apertures. How it might be focused by a lens, right, or how it is focused by a lens. These aren't all hypothetical. These are, yes, you can model these very easily. Okay, but really anything, almost anything you want to model, you can model with this simple model, I would argue, if you're dealing with linear, kind of in the linear region. So we're going to say that our transformation of the wave as it goes along its business, forming your image, will be a sequence of transformations T, which take an input field and map it to an output field, right? And so here I just drew a cartoon picture of some circular pattern of radiation forming a parallelogram type radiation. I just drew that as some random thing, right? It's not very specific. Generally, radiation likes to spread out when it's doing transformations unless you have a focusing element. But it can be any form of transformation like this. So this transformation, I'll also note, I'd like you guys to start thinking about transformations in the real, specific use of the word transformation as a mapping from one function to another. And we're going to do a lot of these transformations digitally, naturally, right, as a class focused on programming and machine learning. So here I'm talking about a physical transformation. Hey, I had a source of light, and then I look at it over there, it's spread out, right? But also, due to physics, but also in your computer simulations, I want to propagate light through my imaging system. I'm going to apply this transformation to this little field at the beginning, and it turns into that, right? Or in a machine learning sense, right? I want to transform all types of inputs of different light patterns into the same type of output via a fixed transformation or a dynamic one, right? So it's really an operation, right? You could implement in code as well. Does that make sense? So I want you to think abstractly about these transforms. Okay, and so we can come up with a very simple model for these transforms, especially as applied to physical transformations, if we make two assumptions about this mapping T. The first is the superposition assumption. So that means T is homogeneous and additive. And so what that means is if you multiply the input by a scalar and then transform it, the output is going to be the same thing scaled, right? So you can scale the inputs. If it's 10 times as big coming in, it's going to be, the output's going to be 10 times as big, right? In a kind of big meaning a scalar multiplicative term. Second is additivity, right? If you put in two things to the transform box, the output is going to be the sum of the two things as if they were put in separately, right? So in other words, things don't mix together, right, in a non-additive way. So if you put in something, get the output, put in something in, get the output, add them up, it's going to be the same as you put both in it together. Cool? So the second big assumption, so that one's fine, right? Linear systems act like that, right? No big shock there. The second big assumption is that we need shift invariance. So this is the same assumption that's used in circuit analysis or, right, any type of signal processing based on these one-dimensional wiggling signals you're probably used to if you're an electrical engineer, where that assumption is time invariance. So if you input a signal into a circuit, you get something, you shift that input by 1 second earlier or later, it'll look the same, right? Which is a very natural thing to observe. Here we're doing the same thing in space. And so we want to use the same assumption, but we needed to obey the same rules with spatial shifting. Right, so if we have an input and we shift it a certain distance, in 2 dimensions, the output is going to be the same thing as it would have been, just shifted. Now that's a big ask, right? Some cases it makes total sense. If I have like a laser beam and I'm making a pattern on the wall, that's a transformation of the laser beam, and I just walk over here, you'd expect it to be the same, just moving across the wall. But in an imaging system where we have finite lenses that aren't so big, right? If I have a picture and then I start to move things and it goes to the side of the lens, right? You might expect the behavior of the lens to change, right? And so we really need to kind of think about that carefully, usually when you're applying these models. And so if we make those assumptions, right? Additivity and homogeneity and shift invariance, then we come with a very simple model. We can describe any black box transformation as, it's in the title, a convolution, right? Which is great because we love convolutions in this class because we're going to soon work a lot with them in our convolutional neural networks. And so what does this really mean? So if you haven't taken signal processing before, I'll kind of walk through it a little bit carefully. So this means that we have any sort of transformation that obeys those 3 properties, right? We're going to put different things into it and get different things out, inputs to outputs. We can model that all with one simple kind of framework. The framework goes as follows. We're going to first say, hey, we have our transformation. Let's put a point source as the input, a perfect point source. That means, mathematically speaking, we're going to input the input to our transformation just to kind of see what's going on and understand it is going to be a delta function. This is a, impulse response is another term for this, or just something with a large value at one spatial location and zeros elsewhere. Okay? And so if we put in a perfect, and so physically this is literally you have some optical or radiation rather scenario and you want to understand it, you say, oh, I'm going to assume these assumptions, these 3 assumptions hold. You make a little perfect point source of radiation. In the optical world, you take a index card and poke a little hole in it and shine light through it, and that's your pinhole source. Or you assume some source of light really far away, right? That you're going to then try to understand how it goes through your lenses or diffracts off different things, right? And so this is, has a very physical manifestation as well. But let's say you have this perfect point source that goes through the black box, you get some output. That output is going to be called H in all of our homeworks, at least. H has different terms. You can call it an impulse response or a point spread function, right? Those are generally what we refer to it in imaging. So this perfect point source, if we shift it due to our 3rd assumption, right, or our 2nd, right, general assumption, we're saying it's shift invariant, so the output's going to shift, but otherwise not change, right? And so we can assume this transformation holds below. So if that's true, then all we need to know to characterize our black box is its point spread function H. As long as we know that, we know everything about the transformation. We don't need to know anything else. Okay? And so the H, like I said, is the system point spread function. And so really what we're after in imaging or in any sort of modeling of radiation in the linear regime are these quote-unquote point spread functions. Right? They can define something you've made, but they can also just define physics. So how light propagates from one plane to the next, you can effectively model with this point spread function that's derived via physics, right? To tell you how much the light's going to spread out as a function of distance. And so the output, like I said, is going to be defined by this point spread function. Like I said, all we need to know is this. And so what we need to do if we have an arbitrary input, right here now, this large circle or a smiley face or whatever, is we need to know that input. And we're going to model this system, we're going to take the input and convolve the input with this point spread function. And that's going to produce our output. So that's this convolution theorem that describes any black box linear system. Okay, and so we can derive that in 3 easy steps. So this is our very quick proof of the fact that given any input, you can model any output, assuming the 3 assumptions I made for a linear black box system. So we started off with the assumption that the output is going to be modeled by a general transformation T, which takes any input in. We can go ahead and use the sifting property of the delta function to rewrite that input just as it's an integral of that input, or rather a convolution of that input with a delta function, right? In other words, if you move a delta function around anything, any function, and sample it, you'll just recreate the original function, right? So this is just like an identity that we use. So then we're going to apply first our linearity property. The linearity property says that we can effectively move this transformation T into here, right? Each of these values of the input can be treated as a scalar. And then the integral is this infinite sum, right? And so we said we can sum up 2 things, right, within a transform, and it's equal to the scaled versions of them outside of the transform. So we're just applying that first assumption here to move this T into the integral equation. And then finally, we apply shift invariance to this and say, oh, we're transforming shifted versions of this delta function. Well, that's the same thing as the output shifted, right? Well, the output shifted is just the point spread function H itself, right? We said if we input a delta function, we get the point spread function out. We input a shifted delta function, we get the shifted point spread function out. So anytime we see this, we can replace it with H. And this is a convolution. This is exactly what I just showed on the previous slide. And so this says we're taking our model any output, we're taking our input complex field and convolving it with whatever point spread function we've determined defines our black box. It's a pretty important, kind of very short but sweet proof that allows us to just model most situations where we're trying to physically propagate radiation or form an image with radiation as a 1 line in Python, or 2 rather. You have to define your point spread function for the situation of interest, and then you do a conv2D, a 2D convolution. Okay, and so if this convolution is like, hey, I forgot what a convolution is, we're going to do it a lot in this class. I'm showing you, each time we do it, I'm going to show you a different way of picturing it or interpreting it. So before I showed you like my drawings of combining 3 numbers and going ahead and shifting and adding them. This is the snapshot from Wikipedia. If you just Google, or it used to be, they keep changing it. But this is another graphical representation of a convolution operation. So if you get confused, I'd encourage you just to look it up again and again, because if you've never seen it, it takes a little bit to sink in what a convolution is. I kind of take it for granted now, but I remember when I was learning it, I kept getting confused about it. And so this is a graphical way to picture the convolution, not of 2 arrays of numbers, but actually 2 1D functions. So you have a function f, let's say it's 0, an array of numbers, effectively, where they're all 0, and then they're all 1, and then they're all 0. And then another one where it's some, negative x type function where it's zeros on the edge. And this zeros on the edge thing is important. We're going to talk a lot about that in this class. It's important to deal with these edge cases of our images. And then in neural networks, there's unique ways to deal with that as well. But graphically, you can, or rather, kind of pseudo-graphically, you can think about a convolution as shifting these 2 functions across each other and then looking at their area of overlap, right? And so that area of overlap is kind of the sum of the product of the 2 functions, right? If you remember the equation for convolution, which I should have put on this slide, right? It's the sum of the product of two functions where one is being shifted sequentially. And so here, right, at this point, we're starting to shift the red triangle. Oh, sorry, I forgot to mention one thing. Weirdly, in convolutions, there's this convention of subtracting for one of the functions, right? You shift it by subtracting some value. And so when you perform a convolution and you're thinking of it in this graphical way, you have to take one of the functions and flip it before you do this exercise. Flip it kind of left to right. Okay? So that's why this triangle is drawn flipped, right? From where it is up here. So they've gone ahead and flipped the red triangle, and then they're beginning to shift it with respect to the blue square and look at their area of intersection. So here they're not quite overlapping, right? So their intersection is 0. So the value of their convolution is 0. Here they're starting to overlap a bit. And so their area of intersection is this orange arrow. It's gone up. And then here they've maximally overlapped, right? And so the area is half the area of that square, right? And so that becomes the maximum value of their convolution. And then it begins to go back down. So there's less, etc. And the same thing is true if you shift the blue square with respect to the red triangle. Right? It doesn't matter which function you shift with respect to the other, you'll recover the same result, which is this commutivity aspect of convolutions. Okay. So you get the convolution ends up being this black curve, kind of this breaking wave type function, for lack of a better term. All right. We will be doing these in 2 dimensions. So that's a one-dimensional functional example. And so you can see just visually this wave-like black curve, kind of like the red triangle, just smeared out a little, or kind of blurred, I would say. If you don't believe me, then here's a picture that I did the same thing with, and we saw this last class or 2 classes ago, where we took the sharp cameraman, we've already seen this, right? And we convolved it with here a Gaussian point spread function in 2 dimensions. And then the end result is a blurry cameraman, right? So kind of the effect of a convolution is this smearing operator, mixing values together, okay? So this blur is caused by a camera lens, right? And so thinking about what we just talked about, this black box picture of like inputs to outputs, I can define a black box as, hey, I'm going to have something I'm going to take a picture of over there at that plane. I'm going to have my camera, and then I'm going to have my picture. That whole process is a black box. So the inputs are going to be whatever appear on the wall over there, and the outputs are going to be whatever appear on my camera. And so if you do that and take a bunch of pictures of different inputs where you know like a high resolution print of it and the output's what appears on your camera, they'll generally look like this, right? And then appear blurry, right? Because no camera is perfect and you'll always end up with generally something blurrier than what you started with. And if I really wanted to understand that, I could say, aha, that's a black box transformation. I'm gonna measure its point spread function. Then I know everything about it, and I can simulate anything I want about my camera as long as I don't move it, right? And so to do that, I can put a point source of light way over there. And then if I put a point source of light there, I'll measure this, right? It's point spread function. Does that make sense? Yeah.
Does that mean that you can always recreate the original based on that?
So can you go from this
So that
and go backwards? Yeah, great question. The answer, as I'll get to in the next couple slides, is no. And the reason why is because deconvolutions are hard. So the opposite of a convolution is what's called a deconvolution. That's where you're trying to unmix the numbers. Yeah. And so when you're trying to unmix numbers, as we'll get into, it's kind of equivalent as, or it is equivalent to trying, 2 numbers have been multiplied and you need to divide off one number from the other, right? And so what if the number you multiplied happened to be a 0? No matter what you do, you can't recover the original number, right? So this is a lossy operation, right, from an information perspective. And as we get into an optimization, yeah, we'll have different ways of defining these, but you can kind of construct scenarios where, as we'll see in the next few slides, this process is less lossy. So you can hope to do a better job at recovering the sharp picture from the blurred one. But generally, if you analyze, you set the problem up and look at it, there's ways to look at it, you can understand how ill-posed it is, mathematically speaking. How much of a good job do you expect to do? And generally, for most scenarios, it's, yeah, pretty tough. Unless you do some tricks, which we'll talk about. Okay, so that's a great segue into this. So here's a real world example. Why do we care about this? Okay, so, and the reason why is you can do interesting things physically and digitally together, right? Which is kind of the theme of this class, and we'll return to it a lot. All right, and so here we're going to talk about 2 point spread functions that are useful, right? And so, not surprisingly, I have a camera and I did that exercise and I said, hey, the images are always blurry, especially if it's not perfectly on the wall, right? It's going out of focus, right? And so maybe there's a way I can make a better camera to do something better than what I just did, right? Make a less blurry image, right? Or recover blurry images if they're slightly out of focus, right? Which was the goal of this cubic phase mask. Okay. And so to kind of understand this, I'm going to walk through just a simple example. And so here have my little picture on the wall, a poster, and I can put up different posters, whatever I want, and I'm taking pictures of them. And I want to be able to get a really sharp image of whatever I posted up, right? Recover an absolute perfect image. And so let's say I have the wall perfectly in focus, and I take the picture, and on the wall I put the letter E, and on my camera sensor I'll see a really sharp E, right, for example, right? And I have a nice camera, and so I have a really small point spread function. So it's a really small blur, and so everything turns out sharp. Whenever you make a camera that has a really small blur when things are in focus, generally when they'll go out of focus quickly, just kind of how cameras work, as we'll discuss. So let's say I put the E, but I didn't perfectly position it on the wall. Now it was a little bit off, right, the wall, because I was being lazy. The point spread function, when things move off the plane of focus, gets blurry, right? And you've probably observed this, especially if you've used a camera that's like a nice digital SLR camera, or you've seen a wedding photograph, right? Usually the thing of interest is really sharp and focused, but then the background's blurry or the foreground's blurry. Or you can just try it right now. Take your camera and try to focus on your hand, putting it close, and you'll see it's blurry just because it can't get to that plane of focus, right? And so I can model anything out of focus at that plane, again, via a black box, assuming that, defocused plane is where my picture will be. And I'll measure, if I put a point source there, a blurred out spot, right? Because it's not going to be in focus. And then you can go even further and move the poster even further, right? And you'll get a really blurry E, let's say, if you move it halfway from the wall towards me, where my camera is still focused on the back wall. Right. And so this is called like what's known as like a shallow depth of field or a limited depth of field camera. And so generally, if you had a bunch of different letters at different depths, you take a picture, as we'll see, and some will be in focus, some will be out of focus, right? Which is not great. You can't see certain things in your pictures. Okay, so just kind of take it. We'll get into this. And so if this is too abstract for some of you, that's fine. We can put a piece of glass here or something here to manipulate our blur. Right, that's not surprising. When you're designing any imaging system, if you put something within the imaging system, it's going to alter the appearance of the image, right? And so specifically, for some of you who know a little bit about imaging systems and Fourier transforms, which some of you might not remember or be comfortable with yet, the blur we observe on any camera is proportional to the Fourier transform of the shape of the imaging aperture, right? And so here, this imaging aperture, in most cameras, it's a circle. And so you can take the Fourier transform of that circular shape to understand the blur impulse response, the point spread function. And so if that's too advanced, just take my word for it that we can put things inside the camera. Here it's a wavy piece of glass. This is particularly called a cubic phase mask. But it's just some small piece of glass for optical systems. You can do the same for ultrasound or for any imaging system, any modality of imaging. And it'll manipulate what we see at the image plane. And generally, when you start to put stuff in imaging systems, it'll always make things blurry. And so you might say, well, why would we want to make our pictures even blurrier, right? And so this, as I'll explain, is a good idea to make something a little bit blurry, as long as you're going to digitally post-process it. And so this blur creates, it's kind of hard to see because the projector isn't great. It creates this V-shaped point spread function with little dots. You can kind of see these little dots here, but it's this V-shaped dotted thing, right? It's kind of this funny point spread function. The shape of the glass is shown to the right. That's its surface profile. It's this funny shaped piece of glass as well. Okay, and so we've created a blurred image. Great. Why is that useful? It's useful because for this particular shape of glass, if you move this E, or you move your point source, the blur won't change. It'll always remain the same. That's a particular property of this point spread function. Right? And so even if something is really out of focus, the E goes really out of focus, I can model its appearance by taking the sharp E and blurring it with the exact same point spread function. And so that's super useful because now what you can do is take a picture of any scene, right, where you don't know how far away things are. They're close, they're far, you never know, right, when you're just using your phone. Or you're just taking pictures of all sorts of scenarios, right? Things will be at different planes of focus, and you'll get a uniformly blurry image, right? Because the A and the B and the C will all be convolved with the same point spread function, independent of their depth. So then all I need to do is try to deblur the image with this deconvolution. And it doesn't matter how far away things are, right? It'll just work across the entire image, and I'll hopefully be able to recover a sharp image. And so that's shown here. So here's the standard picture of some targets at different depths, right, using a regular camera, a regular cell phone camera. This is the picture you'd see if you put that little piece of glass in your camera and took the same picture, right? Everything's blurred, smeared out in this weird way. And then you apply this digital operation, knowing the point spread function of your camera, and you recover a all-in-focus image, right? Everything's sharp again. Okay, so that's one nice example. So the people who invented this, they're pretty smart. They started a company and I think sold this to OmniVision for like $15 million. A while ago now. Because it's a simple way to extend the depth of field of a camera, right? But it only made it into a few systems. And the reason why is because of the challenge of performing an accurate deconvolution. Right? Even though this mask is designed to have a well-posed deconvolution process, it still didn't work too well. And so I don't think it's used that much, but it did make it into some commercial cell phones. Okay, so I'm going to give you one more example of why this is important. And this is, what if you insert some other piece of glass in there that doesn't maintain the same point spread function, depending on how far away things are, but really changes it in a useful way. And by a useful way, I mean changes the blur in a known way that you can measure. Okay? And so one example of doing that, so why would you do that? Well, if you could do that, you can imagine taking a picture and having things be slightly different, shaped or appearances, but in a known way so that you can then tell how far away things are. Right? And so in a regular camera, when things are far away, they just get blurry, right? And if it gets closer, it just gets blurry. So it's hard to tell if something's closer or further via how much it's blurred. But also blurriness isn't a great metric to use, right? Because once things really start to blur a little bit or even more and more, then a eventually they're just really blurry and you can't distinguish how blurry they are. And so what this, well, this is like a review paper. Dr. Morner, who won the Nobel Prize. So this idea was in part awarded to him because it helped lead to his Nobel Prize. So it's another good idea. Again, just about how you blur images. You add a little, what's called a double helix mask. There's different terms for it. Or another piece of glass that takes any point and makes it 2 points. Right, shown here, or here rather. And then as something goes out of focus, those 2 points, you can design the mask, those 2 points will rotate. Right, so you have a little point source of light, and on your camera you see 2 points. If you move that point source closer, the 2 points will rotate this way. If you move it further away, they'll rotate that way. And so you can picture that in three-dimensional space as some point, and then on your camera you have 2 points, and they're like rotating like a corkscrew or like a double helix. Right, so that's why it's called a double helix mask or double helix point spread function. And so what you can do is take pictures that appear kind of funny. Again, it's hard to see because the projector isn't great. But the effect of this little mask, and this is a microscope image, but it also can be used with regular cameras or other imaging systems, is it kind of makes a double image. And then the double image gets weirdly shifted and moved around. But based on how things are shifted, right, these points appearing at different orientations, you can then begin to measure depth. And so this is particularly useful where you have something you're taking a picture of and it's lots of little points. If I take a picture of this room, right, then all those rotations will kind of overlap on each other and be hard to distinguish apart to measure depth. But if it's just a few points and everything else is black, then you'll see lots of double points, but at different orientations, you can just directly measure the angle of those 2 points. And so it's really useful in super resolution microscopy where you're dealing with just little fluorophores that are blinking, for example. So another use of these point spread functions that are being physically created in an imaging system to then try to do something useful afterwards, right? But there are some interesting things that you could do exploring in this direction, right? Again, because it's relatively simple, right? It's a convolution operation allows you to model these effects. One line in Python. Okay? More than one, because you have to do all the other stuff. But in general, like when I say one line, I mean it's like a pretty simple mathematical operation, right? Which is tractable and linear and kind of easy to debug and really get working. So nowadays, most people who are designing these masks are using machine learning to help tell them which masks are better or worse, right? Which is what we're going to talk about in this class. But previously, when they designed these, it was really from a physics perspective, physics-based perspective. So I can tell you, I learned about this when I was in grad school. For this cubic phase mask, they were looking at this space. It's actually a function called the ambiguity function. If you want to Google it, it's cool. But it's a space that defines how well a system can stay in focus, right? A physical two-dimensional or four-dimensional, really, graphical space. And they were saying, well, because you can model how things go in and out of focus by looking at that space. And they say, we want to maximize the coverage of that space. How do we maximize the coverage of that space? Well, it turns out that these cubic functions really have this unique property of maximizing the coverage of that space. So it was really from like a physical insight perspective. This cubic phase mask, I know that people were interested in creating these types of vortex double helix beams, not for imaging applications, just for their general, right, physical interest, right, in neat beam shapes, beam profiles. And then the transition into this imaging space, I think, was a follow-up. So I think they were first designed with lasers and then put in cameras. Okay, so some properties of the convolution. It's communicative, right? You can flip it. Doesn't matter the order. It's associative, so you can perform them in different orders. It doesn't matter when you blur something and then blur it again, right? You can switch the operation of when it was blurred, switch the order rather, and the output will be the same. And it's distributive. So if you add two point spread functions together and then blur an input with it, it's the same as doing that separately and adding it, right? So again, all of these nice linear properties which we just discussed. So again, don't worry too much about the orders of your comms in your Python code because of these properties.